Find the area of the region bounded by these three curves and sketch the region. Here's the trouble you're going to run into on your calculators if you're just like, hey, I've got a graphing calculator, I'm going to be fine, I'm just going to graph everything. Is that these are not functions of x. These are functions of y. So unless you know how to use the parametric mode on your calculator, you're not going to be able to graph these. If you'd like to know how to graph them using the parametric mode, please come by my office and I'll be happy to show you how to use that feature on your calculator. But it's not for here, it's not for now. So we have to do it by hand. So are we all comfortable that these are all functions of y? X is determined if you know what y is. Y goes in, x comes out. Y goes in, x comes out. Here, not so much. But that's just a line, isn't it? Okay, so let's try graphing all of these. Let's start with y equals 0, because that's the easiest one. That's y equals 0, the x-axis. How about x equals the square root of 2 minus y? Uh-oh. What does that look like? Well, if you don't know what it looks like, I mean, you know it looks like a square root function? Okay, you know kind of what those look like? Almost like little half parabolas? All right, just plug in some values then. Let's plug in,
-2.
how about 2? Let's plug in 2 for y. 2 for y. If we plug in 2 for y, 1, 2 for y, what should we get for x? 0. Do you see that's opposite of what we would normally do? You plug in the y value, it spits out the x value, left and right. Let's plug in 1 for y. What do we get if we plug in 1 for y? Square root of 1, which is 1. So if I plug in 1 for y, I get 1 for x. Yeah? How about if I plug in 0 for y? Square root of 2, what's square root of 2?
It's smaller than 1.
Bigger.
Oh.
1.414 square root of 2. So here's 1, here's 2. So when I plug in 0, what did I get? Square root of 2? 1.4, so something like that? We okay with that? Could I plug in y is, I heard -2, I like that one, right? What's -2 if I plug in y is -2? Square root of 4, which is 2. So if I go to -4 on the y-axis, I will be at -2 on the x. And I kind of get an idea of what this is looking like now. -2, right? Sorry. That should have been here. At -2 for y, it's 4 in here. Square root of 4 is 2. So at -2 for y, I get 2 for x. I accidentally put -4. Yes, and it keeps going. I think that's probably enough for us to get an idea of what's happening here. All right, what about the next one? This is my blue one. What about the next one? Plug in 0 for y, what do you get? 0 for x. Plug in 1 for y, what do you get? 1 for x. Plug in 2 for y, what do you get? 16? Yes? Way out here, right? Somewhere way out here. What if I plug in -1 for y? And then -2 for y, way out here again, right? So this looks very much like a parabola, but sideways. It's not a parabola, that's 4th degree. So it looks like this. Oh, shit, I missed it. Oh well. Okay, good enough. We happy with that? Do you see the region enclosed by all of the curves? You sure you see it? There's two of them, right? Do y'all see them? So let's... Hmm? Yeah, you could do this without y equals 0. Let's change it. Instead of this, let's make this easier. Y greater than 0. How about that? Because what does that do? It basically cuts off the bottom half. Agreed? Y greater than 0 means we're only looking up here. So that'll force our region to be this and there, won't it? Questions so far on the setup? A good picture is always where you start with these. You got to have a good, decent picture to go. Now that I've got a picture, I'm actually going to spend a little bit of time trying to make my picture a little bit nicer to look at, just my personal preference. I realize that I'm in a small space there, so I can kind of zoom in on it a little bit. I have a bottom function, this. I've got this blue function that comes in like this. And then the black one looks like this. Right. Now, I'm only doing this to help guide us for the next step, which is to determine whether or not we want to do vertical rectangles or horizontal rectangles. Do you want to draw vertical rectangles or horizontal rectangles in there? Horizontal, why not vertical? Would vertical work? If I draw a vertical rectangle right in here, do I have a top and bottom function? Yes? And it's not the same function, right? It's not wrapping back on itself. So I could do that. But when I get to this point, what would happen? The rectangles on this side change a little bit because now the top function is actually the blue, not the black. Do you agree? Do you see that? So I could do it with vertical rectangles, but I would have to split it into two different integrals. I would have one integral that would take me up to this point, and then I have a separate integral that would go from that point over. Understand? That's too much work. If I do horizontal rectangles, one rectangle should take care of everything. Because the blue function will always be to the right of the black function, right? As I move the rectangle up and down, the blue is always to the right of the black. Right? So that makes sense that we would want to do that. Also, if we're going to use this horizontal rectangle, don't we need this blue function to be a function of y? And don't we need the black function to also be a function of y if we're going to go horizontal? And are these functions of y or x? They're functions of y, aren't they? So it's actually nice that they're already written this way for me. So which one was G? Is it this one right here? That was G. And then this one is F. What do we still need to resolve? The intersections, right? Where they hit each other. I need to see where these two hit each other. These two, right? At y equals 1, right? You can tell. You can tell just by looking. The intersection on the other side. You mean where they hit over here? Is that the one you're talking about?
Yeah, but we can't look.
We're not looking down there, but how would we find that, right? We would need to be able to find that. You would have to set y to the fourth equal to this. And then you'd have to solve this. So you would square both sides. And then you'd probably be in some trouble at that point. So you go to Wolfram alpha. But again, this is something you could do by inspection. Just look. Y is 1, it works. Right? Y is 1, it works. It's 1, yes. But what's the other one? Because there's a negative solution also. Yeah, let me see if I have it here. Yeah, see, on my picture, that's the actual graph. I did go back and do it as y greater than 0. All right, so is that all right with everyone that this one right here is going to be y equals 1? May I set up my integral? All right? Okay, where is it going to be from? 0 to 1. 0 to 1. Remember, 0 is this bottom piece, right? We're going from here to here. 0 to 1 on the y-axis. And then it's going to be something dy. So which one goes first there? The square root one, right? The blue one. Square root of 2 minus y. And then the other one, y to the 4th. You think you could integrate that? Yeah? Basic u sub on this one. Power rule on this one, you're done. But that's where we stop. So far, is this okay? Sketch the region bounded by these two curves. This is a good problem. Sketch the region bounded by x equals sine y. And find the area. Let's see. We have x equals sine y, x equals cosine y equals 0, y equals 2 pi. So we want to sketch the region that's bounded by all these curves, and we want to find the area of the region bounded by those curves. These are functions of what? X or y? These are both functions of y, aren't they? This is y equals 0 is the horizontal line, x-axis. Y equals 2 pi is the horizontal line up at 2 pi. So when I go to graph this, I'm going to draw x equals sine y. So let's see if you can do this. If y is 0, what's x? X is, what's sine of 0? 0. So for this one, if y is 0, x is 0. All right, let's pick some common angles that we're going to be able to know. What if, see, if this is 2 pi up here, this is pi. This is pi over 2. Do we know the value of sine at pi over 2? So if we let y be pi over 2, what is sine of pi over 2? 1. So if y is pi over 2, the x value is 1 to the right. What if I plug pi in for y? What's sine of pi? 0. So the x is 0. So up at pi, y is pi, x is 0. The next common angle that we should know is, what, 3 pi over 2? If y is 3 pi over 2, what's sine of 3 pi over 2? Negative 1. So the x value is negative 1. And then back at 2 pi, we're back at 0. So do you all see that we've drawn this sine curve that looks like this? That's what we've drawn. Now again, if you're outside on the other side of the board and you look at it this way, it's just the sine curve like you normally see it, right? It's just when we draw it as a function of y, it looks kind of awkward. All right, now we're going to do the same thing. We're going to do it for cosine y. So if y is 0, what's cosine of 0? 1. So when y is 0, x is 1. So that puts me here, right? When y is pi over 2, cosine of pi over 2 is 0. That puts me here. When y is pi, cosine of pi is negative 1, so we're here. 3 pi over 2, cosine of 3 pi over 2 is 0. And cosine of 2 pi is 1. So you get this picture. Like that. So see it? Again, if you're on the other side of the board looking in, tilt your head, that's cosine. So what we need to know now is the area between these curves. And I'll stop up at 2 pi, right? I start at 0, I go up to 2 pi. Does anyone see what the problem we're going to run into? What's the problem? With that, I'm hearing different things.
He said no.
I didn't.
It's a negative and positive areas.
Yeah, like if, well, I should probably back up. Are you going to want to use vertical rectangles or horizontal rectangles? Horizontal, right? I mean, there's no question about that. Do you all agree? So if you're going to go horizontal with your rectangles, if you look at this rectangle right here, which function is on the right side? Blue, right? What's on the left? Red. But when you get to the rectangle up in here, what? They switch places, right? So you're going to have to split this up. You're going to have to break it up into one integral that goes from here to here, then another integral that's going to go from here to here, and then another one from here to here. What's that?
It should be the same integral on the top most and the bottom most one. You just have to change the period of which it's integrating.
You're saying what? The same? These should be the same areas? What do you
No,
say?
like the
Oh.
same. Okay, so like the top function or the topmost. There's the top, middle, and bottom. The top and the bottom one are essentially the same integral. It's just the same.
Oh yes, yes. Okay, yes, that's exactly right. The integrand, the part that's inside the integral, the integrand for this one and this one will be the same. It's the limits of integration that'll be different. Yes. So why don't we call this one down the bottom integral 1, this one here integral 2, and this one here integral 3. What is it that we need if we are going to proceed? What pieces of information are we going to still need to get here? The intersections, right? We need to know where that hits, where that hits. Well, we already know that's 2 pi up there, right? So we know we're going to go from 0 to something, right? Then from that something to something else, and then from that something to 2 pi, yeah? Okay. So how do you figure out where these two intersect each other? Set them equal. We're going to set sine y equal to cosine y. When does sine of y equal cosine y? Pi over 4? 3 pi over 4? Yeah, you can just go back to your unit circle. Sine and cosine are the x and y coordinates, aren't they, on the unit circle? So you're just looking at where the x and y coordinates the same. It happens here at pi over 4, right? The x and y coordinates are root 2 over 2, root 2 over 2. And then it happens again down here at 3 pi over 4. No, that's not 3 pi over 4. That's 5 pi over 4. I think so. If you said 3 pi over 4, sorry, that's incorrect. That is over here. They aren't the same there, are they? They're off by a sign? Sine and cosine are off by a sign? Okay, so that doesn't count, but this one does. 5 pi over 4, they're both negative root 2 over 2, negative root 2 over 2. So only at pi over 4 and 5 pi over 4 they equal. And that corresponds to these 2 points. Understand? So this happens when y equals pi over 4 or 5 pi over 4. There's actually an infinite number of solutions because you could just keep going around, but we're only looking between 0 and 2 pi. Questions on those? Are we ready to set this up? Okay, let's set it up. It's going to be, I'm going to have to erase this. Just remember the blue one is cosine, the red one's sine, right? Blue is cosine, red one's sine. So integral 1 plus integral 2 plus integral 3 equals, integral 1 goes from where to where? 0 to pi over 4. And it's going to be the one on the right minus the one on the left, which would be, it's cosine y minus sine y. Everyone agree? Yes? Plus, now the next integral goes from, this time, pi over 4 to where? 5 pi over 4. But it's flipped over, isn't it? It's the sine y minus cosine y dy. And then integral 3 will be the same integrand here. This is what Ron was saying. Same integrand, just different limits of integration. So integral 5 pi over 4 to where? 2 pi of cosine y minus sine y dy. I'm out of room. Could you integrate each of these? Yeah, those are pretty simple antiderivatives. And then you have to plug in fundamental theorem of calculus for this, get an answer, get an answer, get an answer, add them all up, you're done. Dot, dot, dot. That means we're done. Last one. Do you get the basic principle of this, though? You've got to figure out what the region is, which is going to require some graphing skill, and then determine your limits of integration, plug in, you're done, right? All right, so let's try this. Sketch the region bounded by these curves and find the area. Y equals e to the x. Y equals 2e to the negative x plus 1. And then x equals 2. Just by looking, do you think you're going to use vertical or horizontal rectangles? Just by looking at what's up there. Vertical, because these are in terms of, they're solved for y, so they're functions of x. That doesn't always mean that, but that's what you're leaning towards here. So, drawing time. I've got a few here that I'd like to do. X equals 2. That's an easy one, right? That's a what kind of line? X equals 2. Vertical line going through 2. That's supposed to be straight. All right. E to the x, that one's not so bad, right? E to the x, we should all know what that looks like. 1 goes like this. Tapers down like that. And finally, 2e to the negative x plus 1. How about that one? 2 over e to the x plus 1. Is that not the same thing? It's the same thing. So what happens is, I'm trying to think if there's a number we could plug in that would be real easy to pick up on this. How about x is 0? If x is 0, what do we get? We get 3, right? E to the 0 is 1, 2 over 1 is 2, 2 plus 1 is 3. So at 0, we should be up here at 3. And now it's just a matter of trying to figure out what happens. As x gets huge, what happens? As x gets huge, this thing blows up.
0.
That goes to 0 plus 1. So the whole thing gets closer and closer to 1, doesn't it? As you go out to the right forever. Like this. Closer to 1, where's 1? 1's right here. So I'm getting closer to 1 as I go out to the right. Something like that. What does it do as I go to the left? If this right here, if x goes to negative infinity, e to the negative infinity actually becomes very small. And 2 over a very small number becomes a huge number. And so this becomes infinite, so it looks like this. Another thing you could have done, probably easier, is just to realize that e to the negative x is the reflection of e to the x over the y-axis. Much simpler to look at that way, but it's done. Do you see the region bounded by these curves? Yes? This it? Oh. Yes, this is it right here. Vertical rectangles going to work? If I draw a vertical rectangle in here, is it always going to have the same function on top as the bottom, and then same top and bottom the whole way through? Blue on top, yes. Black on the bottom. Blue on top, black on the bottom. So that should work. We need to figure one thing out, though. What's that? The intersection. We need to figure out where these two hit each other, right? The right side, we already know where it stops, don't we? We know that this integral goes from something to 2, right? And then it's 2 functions. What's going to be the one on top here? The blue one, e to the x, and the bottom one, 2e to the negative x plus 1, right? So we've got all of this already set up. We just need to figure out what this bottom limit of integration is. So we shall now do what to find their intersection? Set them equal to each other. And when we say them, we mean the two that hit each other, right? The blue and the black one. So we're talking about these two. So we set e to the x equal to 2e to the negative x plus 1. What would you like to do to that? Solve that for x. Natural log, I hear natural log a lot because natural log will actually, if I put natural log together with e, it'll wipe out and the x will pop out. Problem is on this side, when I do natural log, all of this is trapped in natural log and I can't simplify that. So it's going to trap x over here, unfortunately.
Can we change that one to
Change it, what?
e to the x over e to the x?
Change the 1 right here? Is that what you're talking about? Yes, you could. I think you're on to what you should do here. I'm going to write it this way, back like this. Yeah, you can just basically multiply everything, both sides of the equation, by e to the x to clear the fraction. So what happens if I multiply this by e to the x? E to the 2, wait a minute, hold on. No, that's right. No, I'm saying, but that was that problem on the test, right? E to the 2x was e to the x times e to the x. E to the x squared. Okay. We all know that now, right? We won't ever forget that. E to the 2x is equal to e to the x squared, right? We got that hardwired now, I hope. What do I get here when I multiply both of these by e to the x? 2, and then plus e to the x. All right, that's good. You cleared fractions. Now what do you want me to do? It's a quadratic form. This is basically a quadratic form right here. This, if we move everything to one side, looks like this. E to the 2x minus e to the x minus 2 equals 0, which is really e to the x squared minus e to the x minus 2 equals 0. So this is a quadratic form equation. Does it factor? Can this be factored? E to the x minus 2 plus 1. Do you agree with that? Do you all see that this is a quadratic in e to the x? Yeah? That if I multiply these back out, I should get this? Some people prefer it when I go in here and I make a substitution. I say u is e to the x. If I do that and rewrite this, the problem becomes u squared minus u minus 2 equals 0. And then I go through and just do like college algebra factoring on that. I'm doing the same thing. I'm just skipping all the intermediate stuff of this. Because this would factor to be what? U minus 2, u plus 1. And u is e, so this is it right there. So now that I have that equal to 0, I set each one equal to 0. I get one answer, e to the x is 2. The other one is e to the x is negative 1. How do you solve for x? Now you can come in with the natural log. You can come in and take natural log on both sides. So what do you get here if I take natural log on both sides there? You just get x is natural log of 2, right? Taking natural log on both sides. And then the other one, when I take natural log of e to the x equals natural log of negative 1, you get x is equal to, natural log of negative 1 is undefined, right? Undefined. Can't put a negative in a natural log. So you only get one answer. You only get one solution. Does that match our picture? Those two only hit at one point, didn't they? So the answer is natural log 2. So that should finish up the setup for the integral. Right? It should be integral natural log 2 to 2 of, I forgot already, was it? It was e to the x on top, e to the x minus 2e to the negative x plus 1 dx. By the way, could you integrate that? You should be able to, right? Antiderivative e to the x is itself. Here we just distribute the negative, do it term by term. You should be able to integrate and plug numbers in, and it'll work out nice. That's the end of that problem, though, as far as what I'm going to do.
Do we stop here in the homework, or
Do we what?
do we stop at this point in the homework, or do we stop every day?
If you're going to want to try and match the book's answer, you go through everything. What I would do if I were doing homework is just set everything up first, get it all set up for time's sake, and then go back and start evaluating them. Or do them all at one time. All right, you all look very, very exhausted today. Are y'all okay? Y'all just look all dragon. Not like fire-breathing dragon either. I mean like dragon. I have a stack of papers. Where are they? Are there any other stacks of papers floating around? So if you don't have, if you want to come try and retrieve your stuff, you can. Try and do your homework out of this section. See how it goes. You know what?
In the notes.
Is it at the end of notes?
It should be.
Let me see, maybe not. Okay, let me tell you what to do then. This is off of page 369. Number 1, that's it, no. 1 through 19, odds. It's not so much. So on the first two, like numbers 1 and 3, they give you the sketch. So it's just a matter of you interpreting the sketch and setting up the integral, and then finding the area. The rest of them, sketch the region, decide either whether you're integrating with respect to x or y, which means are you doing vertical or horizontal rectangles. Draw a typical approximating rectangle. So they want you to like actually draw out. You don't need to necessarily do that, but if you want to, try and get this picture set up. And then find the area. See how that goes.
What was the question right here? Like right here. So you put a question mark. I'm not sure why.
Okay, hold on. Let me turn my camera off. That's right. Excuse me real quick.